So our vertical asymptote is x equals 1. And then our horizontal asymptotes, do you guys remember how the horizontal asymptotes come about? That's what happens at the very far ends. Right now, this is top-heavy. At top-heavy, the numerator of the function is going to get much larger, much faster than the denominator when we're talking about the very ends of the graph. When we're talking about infinity, we're talking about very large numbers. So the numerator is going to get much larger, much faster than the denominators. So there's no horizontal asymptotes on this one when it's top-heavy. So we write none. We do have something called a slant asymptote. Okay, before we get into a slant asymptote, I want you guys to graph the function right now in your calculator, and I want you to take a look at what the picture looks like, and then we'll talk about, you'll visually be able to see that there's this line that it kind of converges to. So you should have graphs that are overlapping each other when you type in both the original function and the factored form of the function, because they should be equivalent. Okay, so it should be identical. Do you guys notice that there is kind of a line that the graph converges to at the very ends of the graph? All the way to the right, all the way to the left, as it keeps going. There's kind of a line that it converges to. Can you visually see that? Just confirm that. Yeah. Okay, that's the slant asymptote. Okay, that we can get the equation for that by dividing the polynomial, dividing the function, okay, and seeing what it is as it's divided. Okay, and if you guys remember from last semester, to divide two polynomials, you can do it two ways. You can do it using long division if you feel like, or if it's just a binomial in the denominator, you can just use synthetic division to do it. So we're just going to use synthetic division because it's the simplest. And quite frankly, I'm not going to give you anything that's any more complex than this to divide out, because that's kind of outside the scope of this chapter. So the denominator right now, so we're going to divide this, the numerator by the denominator. And we're going to do that by synthetic division, and that's going to kind of lead us directly into what the slant asymptote happens to be. Remember, we put the opposite sign of that in the penalty box? So then we put the coefficients 2, -2, -4. Drop down 2, right? Multiply them. 2 times 1 is 2. Add it, 0. 2 times 1, 0, -4. That's your remainder, remember, -4. The slant asymptote comes from the quotient of the division that we just did. Okay? Not the remainder. The quotient. Not the remainder. Okay? So the quotient is 2x. If you remember that. Remember, this 0 is the constant term, then we go up to the linear term, then we go up to the quadratic term. Slant asymptote is 2x. We need to write that as an equation. Okay, so it's y equals 2x. And then we need you to graph that on the graph itself as a dashed line, because it's not technically part of the graph. It just gives us a better visual of what actually happens at the ends of the graph. So we start at 0, go up to right 1, up to right 1, down 2, left 1, down 2, left 1, and it's a dashed line. That's our slant asymptote for our function. Okay? We're going to graph our vertical asymptote at x equals 1. As well, graph it as a dashed line. One way you can check to see if your slant asymptote is correct, if you type it in to your calculator as 2x, you're going to notice that when you graph it, it should go right down the center of that, and the graph should converge at the end. It's a double check to make sure you did that part right. Okay? Does that make sense? It's kind of new, a little bit. Okay. Then we, after we do the asymptotes, then we do the table. Remember, I asked you to do to the left, to the right, of the vertical asymptotes. So to the left would be 0, to the left would be -1, to the right would be 2 and 3. And we have our calculator do that work for us because we all know that we can evaluate it ourselves. So you just type in -1, enter, 0, enter. You know, you could put in 1, enter, and then it's going to show that asymptote represented. And then the vertical asymptote, and then 2, and then 3. Remember, we put it in at y1 up here. So then we can write those down. So we get -1, 0, 0, 4, 2, 0, 3, 4. And we plot those points. Two, 0, and then 3. And then when we graph our function, we want to make sure to give it nice, smooth, and converging to those asymptotes to make sure that we have the right kind of picture. Okay? That's what it's going to look like. From that, we answer the other questions. Okay? Let's answer. There's no maxes and mins based on what the picture looks like. Then there's x-intercepts. That's where y equals 0. So we can go back to the factored form of the function, and we can set that equal to 0 and solve it. So I'm going to do that right here. For that fraction that equals 0, the numerator has to be 0. So we can just set the numerator equal to 0. And what two values make that numerator equal to 0? 0 product property, we get x is 2, and we get -1. So we have two x-intercepts. We have a point 2, 0, and we have a point -1, 0. Y-intercepts, and that makes sense on our graph. 2, 0, it's there. -1, 0. If you would have noticed that we actually already found them, so you didn't have to do all that work because it was represented in your table already, if you get lucky when you pick them. Y-intercept, it's at 0, 4 for our y-intercept. It's where x equals 0, and how do we find that? We substitute 0 in for the x value, and we calculate what the y value is. Domain now, it splits at 1, right? Splits at x is 1, so we have to write that. We have to write our domain, and we have to split it at 1. Okay. I didn't put a spot for a range on this, but let's do the range. Range up and down, does it go down forever? It goes down forever. There's no, it goes up continuously all the way to infinity and keeps continuing to go up. So it's negative infinity to positive infinity on this one. Okay? Okay, on this next function, we changed the problem. I gave you the original, okay, and then I factored it for you, because I don't want to focus on that part at this point. I want to focus on something that's new. You'll notice that when it's factored, there's a common factor in the numerator and denominator, correct? Okay. When we write it under the factored form line, I want you to reduce that. Okay. But when you reduce that, I want you to state that that factor that you removed, or the value that x can't be, the restriction on the domain from that factor that you removed. If you remember doing that earlier. So right now, when you write it in factor form, I want you to reduce. I want you to reduce it. So it's -2x squared all over x plus 3, x minus 3. But I also want you to state that x cannot equal -1. Okay? Because that's still very important information. All right, now what I want you to do, let's talk about vertical asymptotes. Before we talk about vertical asymptotes on this, put it in your calculator, graph it, and let's see what the picture looks like, because something very interesting happens because we removed that factor. You guys will notice that if you type in both the original and the factored form and the reduced form, the graphs look identical because they're on top of each other when they're graphed. Okay? But the thing that's different, if you look up at mine, you'll notice that at -1, for the original, there's an error because it's not in the domain of the original function. If you remember, the original function had a restriction at -1, had a factor of x plus 1 in the denominator, which means x can't be -1. Follow that? When we reduced the function, and we put it in the second one, that restriction, that factor is no longer in there, so we don't have a restriction on the denominator any longer. Okay. That, guys, is called a removable discontinuity. That's the fancy way to say it. The normal way to say it is it's a hole in the graph when it's actually graphed. You might think that looking at the denominator of the function after it's factored, you might think that there's going to be a vertical asymptote at -1. But in the picture of the graph, there is no vertical asymptote at -1. There's a hole in the graph at -1 right there. Okay, and we're going to talk about finding that in just a second. Right? So right now our vertical asymptotes, we have to look at the reduced form. X is equal to -3, and we have x is equal to 3. Horizontal asymptotes, this function in its original form is balanced. If you recall from yesterday, if we have a balanced equation, the horizontal asymptote is the ratio of the leading coefficients, or you take the leading coefficients and you write it as a fraction, and that is your horizontal asymptote. So it's y equals -2/1. I would want you to simplify that, of course, in your final answer. Y is -2. That comes from the ratio of the leading coefficients, the highlighted portion. Does that make sense? Okay. Slant asymptotes, there's none. There's not going to be any slant asymptotes when it's balanced. Okay. Although we just introduced this other concept called the hole in the graph, and we're going to talk about finding that. The x-coordinate of the hole comes from the factor in the denominator of the original. So the x-coordinate of the hole is -1. It's the restriction on the domain that gets removed. The y-coordinate of the hole we have to calculate. If you look at your calculator with the two functions typed in, we evaluated it at -1 for the first function and we got error. That's because that factor was still in the denominator, that x plus 1. When we reduce the function and type that in, we're able to get a value for our y-coordinate because we removed that factor from the writing of the function. Okay? That's how we find the location of the hole, the y-coordinate of where the hole is. You take the factored form and you put the x value of where that hole exists, and you evaluate the function for that x value, and that's how you get your y value. In this case, it's 1/4. That's an important part of the graph, -1 1/4, that you have to note, and you do that by using an open circle. Okay? To represent that the graph gets really, really close to it, but it's not going to get it, and it's just a hole in the picture. And you need to put those when there is a hole. You need to put the open circle. I'll be looking for that specifically. Okay? After we find all that information, the asymptotes, and if there's a hole, you find the hole. Okay? Then we do the same thing that we did yesterday. From there, it's pretty similar to what we did on the previous graph. You do your x, y table. You make sure you graph your asymptotes. Pick 2 to the left